Hello, in this video we're going to look into the chemical properties of alcohols. In the previous video we had looked into the general formula of alcohol, which was CnH2n plus 1OH. We'd also looked into the 1 degree, 2 degree and 3 degree alcohols. We had also discussed about the physical properties of alcohols, and we're focused on the intermolecular forces of attraction, and in the case of alcohol, this force of attraction was hydrogen bonding. We'd also compared the physical properties of alcohol and alkanes, and we had found that alcohols have got hydrogen bonding within them because of the presence of oxygen within an alcohol molecule, whereas alkanes are non-polar compounds, therefore they would just have London forces or van der Waals forces within them. So the properties of alcohols and alkanes we'd compared. So please refer to the previous video if you want more information about the physical properties. Within this video, we are going to look into a few of the chemical properties. We'll start off with combustion. Alcohols burn very easily, and it's facilitated by the presence of the oxygen within an alcohol molecule. So consequently, alcohols tend to burn completely. They burn very neatly, and they produce mostly carbon dioxide and water vapor. The reaction is exothermic. A lot of energy is released, and as the number of carbon atoms in the alcohol chain increase, the quantity of heat released per mole will also increase. And therefore, alcohols are a common additive to petrol in order to increase the heat released from the alcohol that's burnt in the cars. So that's the combustion property of alcohols. You would need to write this equation down when you do the calculations for energetics, especially Hess cycle. The second set of reactions that we're going to focus on here is the substitution reactions of alcohols to form haloalkanes. So haloalkanes are those which contain, if I give an example, which contain a halogen attached to an alkyl group. So alcohols are CH3OH. You've got to replace the OH and put in a halogen instead of that OH. So you using the substitution reaction. The reagent that we use is concentrated sulfuric acid and sodium halide. Now the reason why you do that is because the HCl that is needed for this particular substitution is prepared in situ. Now if I show an example for HBr, then I would need to replace the OH group with Br. So in this example that I'm going to show in this video, I'm going to replace the OH with Br. So in this case, HBr is prepared in situ. Situ means it's prepared while the reaction is going on. So you would literally take in the test tube NaBr and H2SO4, and this is concentrated H2SO4. So when you react it, you would get HBr being produced in situ. So while the reaction is going on, it's being generated. So you're not adding HBr separately, and this is an important point to note. So when you write down the overall reaction, you would show NaBr plus H2SO4 in the reactant, and you've got NaHSO4 being produced here. That is written here. So far we've looked into that set of reactant and that set of products. Now let us see where do we get the remainder of that equation. So that would take to the next equation. So this reaction happens in two steps. In the second step, you would replace that OH with the Br. So OH and H are eliminated as H2O, or you can say OH is substituted or replaced by Br. So where you had the OH functional group, you would now get an halogen there. So you've converted an alcohol into an haloalkane. So it's very important in organic chemistry to keep track of the route maps. So far we have looked into that you can convert alcohol into carbon dioxide and water, and in the previous slide we'd looked into the combustion reaction. So that's one route. The second conversion we've just looked into is converting an alcohol into haloalkane, and that is with a reaction with HBr. But remember, HBr is not produced, it's not taken originally, it's produced in situ. So in situ production of HX. So those are the conversions that we've looked into so far, and now you can see the ones that we've not looked into, we've got the circled ones coming from equation 1. The rest of those come from equation 2. So this is coming from equation 2, that's the alcohol. Then you've got 2-bromopropane is coming from equation 2. And you've also got water, which is coming from equation 2. So you write these two equations, then you add them up, cross out those reagents or products that are common on both sides, and then you add up the reaction to get the overall equation. So be mindful what is being asked in the exam. Have you been asked for step-by-step equation, or have you been asked to show the overall equation? So that's very important to identify by reading the question very carefully. The next chemical property we're going to look into is the dehydration of alcohol to form alkenes. In this reaction, you would use concentrated sulfuric acid or phosphoric acid, and you would heat it. It's warming under reflux. I'll talk about reflux in a minute or so. The type of reaction we use is the acid catalyzed elimination. That means the sulfuric acid or the phosphoric acid is going to act as a catalyst, and you're going to eliminate something. Because we're talking about dehydration, dehydration means you're talking about the removal of water. So you're removing a water from alcohol. So that's what's going to be eliminated. And therefore, the role of sulfuric acid is a dehydrating agent, and it's also acting as a catalyst. It's a very interesting reaction, and it's got huge potential to save fossil fuels because we use alkenes. Now, when you dehydrate an alcohol, you're going to get an alkene, and the alkene is the feedstock for to form polymers. Generally, you get alkenes from fossil fuels. So fossil fuel, you'll do fractional distillation to get the different fractions. The longer hydrocarbon chains can then be cracked, and one of the products of cracking is alkene. And alkenes are then used to prepare many important products, and one of those are polymers. So this reaction is another way of producing alkenes without relying on fossil fuels. So let's look into the dehydration of propanol. So if I take propanol, I'm just going to show 3 carbons here attached to OH. So if I'm just using the hydrogens, if I show the hydrogens in that format, and I have got concentrated H2SO4 written on top here, what would happen is you need to remove the OH. Right, so you're going to remove water molecules. So water is HOH. So if you think I need OH I've got from the alcohol, where am I going to get this next hydrogen? It's important to note that the next hydrogen would be obtained from the neighboring carbon. So you've got to check the neighboring carbon atom. So that's the carbon which is holding the OH. Next to it is the neighboring carbon. So it's this carbon. So that's your neighboring carbon. So it's from this carbon that you remove a hydrogen. So let's take out this hydrogen. So H and OH combine to give you water. Now let's just write down what's remaining. So we've got CH, CHH. Now we've removed OH from there, we removed H from here. Carbon should always be surrounded by 4 bonds. So 1, 2, 3, you get a double bond here. So you get propanol, propane 1-ol got converted to propene. So that's the dehydration of propanol. So you get an alkene by this reaction. Now what about butane 2-ol? So if you look at butane 2-ol, so 1, 2, 3, 4 carbon. On position 2, I've got OH. That's what the name butane 2-ol implies, that the OH is on the second carbon. Now if I react it with concentrated H2SO4, we'll have the same removal of water, but now the neighboring carbons, you've got 2 neighboring carbons. Therefore, if we remove carbon from, or the hydrogen from this particular carbon, you could get a product which looks like this. Right? So you get a product like this. So this one would be but2ene. If I remove the carbon from this, the hydrogen from the first carbon, I would get the product looking like this. So I've removed. So this becomes but1ene. So you get a mixture of 2 products. Now, a very common exam question could be to show the 3 isomeric structures formed by the products of dehydration of butane 2-ol. And generally students get confused because you would think, actually, I've only got 2 isomers here. But remember, but2ene could exist as a E and a Z isomer. So you've got to be very vigilant of that, that's a double bond. On the carbon-carbon double bond, you've got 2 different groups. Therefore, this compound can exist as a geometric isomer as well. So when you dehydrate 2-degree and 3-degree alcohol, they will give you more than one product, because when the double bond can be formed between 2 different carbon atoms. So that's quite a tricky one to remember. And also remember, the isomers are not just the isomers of the products that are formed, but also explore some of the geometric isomers. You would be asked about to write down the mechanism for this reaction. So notice here you've got the alcohol, it's got lone pair. It attacks the H plus, which comes from the acid. The H plus has now joined the bond, has formed a bond with oxygen. As a result, it acquires that plus charge. Due to that, it takes the electron pair from the carbon and you get H2O released now. And then the carbon becomes positive charged, due to which it takes the electron pair from the neighboring carbon, and therefore H plus is then removed again. And you can see that H plus is regenerated at the end, and that's why you can say that the acid acts as a catalyst. It's regenerated, it's not utilized in the equation. So far in this video, we've looked into some of the chemical properties, we've looked into combustion, we've looked into the substitution reaction to form haloalkanes, we've also looked into the elimination reactions. In the next video, I will be exploring oxidation reactions. Thank you for watching.